It cost $10 million, weighs 70 tons, and was built to survive the deadliest weapons on Earth. It is now being destroyed by a $500 machine, exploiting a flawed tank engineers have never been able to solve. The main battle tank is engineered for a single purpose: to dominate contested ground through a balance of firepower, speed, and protection. Its 120mm smoothbore gun, firing at over 1,600 meters per second, can pierce half a meter of steel from 2 kilometers away. But firepower alone is not enough. Diesel engines delivering 1,200 to 1,500 horsepower drive these 70-ton machines, achieving 20 to 25 horsepower per ton, enough to keep pace with mechanized forces and maneuver across rough terrain. Frontal armor, layered with steel and advanced composites, is designed to withstand the world's most powerful anti-tank rounds, while every angle and thickness is calculated for survival. Tanks operate within combined arms formations, but their own design, every kilogram, every horsepower, reflects a relentless focus on outlasting and outgunning any threat on the modern battlefield. Small drones arrived on the battlefield looking more like toys than threats. Early models barely registered on radar, their carbon fiber frames reflecting less energy than a flock of birds. Heat sensors struggled to spot them, too. Brushless motors and low-voltage batteries gave off only a faint thermal trace, nothing like the roaring engines of a tank. Military analysts checked the numbers: 2 kilograms of lift, a few hundred grams of payload, and a range measured in minutes, not hours. It was easy to dismiss these quadcopters as fragile, short-range gadgets, more likely to crash than to cause real damage. But the real surprise came from the world outside the military. Shenzhen's factory floors churned out millions of motors, batteries, and flight controllers, all designed for hobbyists and weekend racers. A new drone could be built, tested, and upgraded in weeks, not years. Open source autopilot code, modular parts, and a global online community turned every failed flight into the next design improvement. While tanks waited for procurement cycles and bureaucratic sign-off, the drone world moved at the speed of a group chat. The overlooked, underestimated drone was evolving faster than any defense planner expected. The question wasn't whether these machines could be dangerous, it was how quickly they could learn to be. Tank armor is a study in priorities and trade-offs. Every kilogram matters, and the thickest steel is reserved for the places most likely to be hit: the front and the turret face. But protection isn't spread evenly. The roof and rear are kept deliberately thin, often just 20 to 40 millimeters of steel and composite, because adding more would tip the balance. Heavier top armor would raise the center of gravity, slow turret rotation, and overload the bearings that allow a 70-ton machine to swing its gun with precision. The turret ring, a critical target, must remain exposed enough to move freely, but that very geometry creates a tempting approach angle for threats from above. This is not a failure of engineering, it is a calculated compromise, rooted in decades of battlefield statistics. Almost all anti-tank fire has come from the ground, not the sky, yet that leaves the roof vulnerable to a very different kind of attack. A shape-charged warhead, even one as small as 30 millimeters across, can punch through roof armor with a margin to spare. The physics are unforgiving. A focused jet of metal, formed by explosive force, can penetrate 6 to 8 times its own diameter in steel. When that jet comes straight down, the thin roof offers little resistance. Suddenly, the problem shifts from surviving a frontal duel to defending against attacks from above. The tank's greatest strength, its heavy, forward-facing armor, becomes irrelevant when the threat arrives vertically, exploiting the very compromise that once defined its survivability. A $500 drone, built from off-the-shelf parts, has become a repeatable weapon. Brushless motors, once reserved for hobbyists, now push over 2 kilograms of thrust for less than $20 each. Lithium polymer batteries keep quadcopters airborne for 20 minutes or send them plunging toward targets at speeds that armored vehicles can't match. Open source flight stacks like PX4 and ArduPilot have turned these drones into autonomous strike platforms. With simple code, a builder scripts flight paths, loiter patterns, and terminal dives, with no pilot required. Commodity cameras designed for smartphones feed live video to onboard computers. A $35 Raspberry Pi or Jetson Nano can run neural networks that spot a tank, lock on, and trigger a warhead at the right moment. Shenzhen's factories supply motors, frames, and controllers by the pallet. Community forums and GitHub repositories share build guides and mission scripts, making assembly fast and accessible. Now, it's about numbers and iteration. Swarms, coordinated by open source algorithms, overwhelm defenses and force a new kind of adaptation. Every new defense against drones comes with a cost. Hardkill active protection systems, once tuned to intercept missiles and rockets, now fire smaller, faster interceptors aimed at quadcopters darting overhead. These upgrades demand dual-frequency radar and split-second response times, but even so, a diving drone at 20 meters per second can slip through the net. Electronic warfare teams add another layer, jamming GPS and radio links to confuse or freeze a drone mid-flight. Yet, as navigation chips grow smarter, many drones switch to inertial guidance, pressing on even when jammed. Some crews bolt on steel or composite plates above the turret, trading a 30% drop in roof penetrations for an extra ton of weight. Others stretch mesh cages across the top, hoping to detonate warheads early, but at the cost of a higher profile and harder escape. To fill detection gaps, engineers stack radar, infrared, and acoustic sensors into a single, layered suite, each one adding complexity, each one with its own blind spots. Defense is possible, but every new measure means more weight, more power drain, and more decisions for a crew already fighting the clock. Directed energy weapons now loom over the contest, lasers and high-power microwaves promising to burn drones from the sky or fry their circuits mid-flight. On paper, a 150 kilowatt laser can cut through carbon fiber at 1 kilometer, and a microwave burst can disable swarms in a single pulse. But every new weapon brings its own limits. Generators must deliver hundreds of kilowatts on demand, cooling systems must shed massive heat loads, and one missed sensor fusion can open a fatal window. The real battle is now fought in milliseconds. How fast a sensor can spot a target, how quickly software can decide, how much power can be routed before the system overheats. The tank is back in the workshop, not as a finished answer, but as a new engineering puzzle. The next breakthrough will not be a single fix, but a race to solve constraints that no amount of armor can ignore. Every new breakthrough resets the balance. Today, a $500 drone can rewrite battlefield logic in a single flight. The real arms race isn't about armor, it's about adaptability. What would you bet on next?